All right, this is Mr. McMurray, and we're back talking about buoyancy a little bit. We just talked about Archimedes, and he's basically came up with the idea that when you put something in water, has a buoyant force pushing up on it that's equal to the weight of the fluid that it pushes out. Okay, so for example, let's see if we understand that. It sounds pretty simple, but let's look at an example. Say we have a weight over here, and it has a mass of, let's just say, 30 grams. Okay, so it has a weight on the scale here of 30 grams. Actually, we have changed that by newtons. Let's just change it to 30 newtons, okay? But 30 grams, let's just say 30 grams, okay? A 30 gram weight. It's pulling down on this. Now, the pan over here has nothing in it, so we're going to say it's empty. Okay, it has mass of 0. If we put the weight underwater, it displaces water because it's full, so the water has nowhere to go except to roll over here into this other pan. All right, and if we measure this water, let's just say it weighs 20, well, let's just say there's 20 milliliters of it. And how many grams would that be? Well, we know that milliliters and grams are the same for water, so it's going to be the same. So this would be 20 grams. So if this weighs 20 grams, the weight by itself basically weighed 30 grams. So what happened to the extra weight? Well, here's the deal. All right, over here we have 30 grams times the acceleration of gravity, 10 meters per second squared. And so we have this force of gravity, which is basically 300 newtons pushing down on this. All right. Now, we know now that we have, when this is in here, first of all, what kind of force of gravity is pushing down on it? Still 300 newtons, okay, of force pushing on it. But we know that it replaced a buoyant force. The buoyant force on it is equal to the weight of this water, which is 20 grams, okay? And 20 grams would have what kind of force? This is a buoyant force pushing up on it. 20 grams, to make that a force, we'd multiply it times G, 9.8. All right, and that gives us 2 or 10 roughly. And so we would get 200 newtons pushing up, okay? So this one here, this weighs, the water weighs 200 newtons, okay? So this up here would read 20 grams, okay? All right, and 20 newtons of force down. Over here, we have 30 newtons, 300 newtons pushing down. We have 200 newtons pushing up. Okay, so which force is greater? Gravity pushing down. It's greater by 100 newtons. And so the scale up here would read either, if it was in newtons, it would be 100, or if it's in grams, it would be 10 grams. All right. And so the total forces here, we got 10 grams and 20 grams, and over here we have 30 grams and 0. Again, it all balances out because this weight displaces water that weighs the same amount as it does. Okay, now, is this thing going to float or is it going to sink? If we were to take this hook off, it would sink because you still have a net force of 100 newtons, all right, pushing down on it, and it would sink. As long as it's hooked here, it will weigh this. But notice that if you're just taking the weight of this, it's 30 grams or 300 newtons force pushing down on it. You put it in here and it only feels 100 newtons. So it reduces the force on it. This is one reason why when you do water aerobics, it's gentler on your body because you have a buoyant force. It's canceling the effects of gravity. And so when you run and move, your joints are not under as much force acting on them. And so therefore it's a lot less painful, and it's especially that's why a lot of times you see older people and stuff doing this, because it's less likely to do damage to their joints. All right, now, so let's talk about buoyancy and floating again for a second. All right, if we have a mass of iron, doesn't matter how much, let's just say it's 100 grams, okay, 100 grams. If we put that 100 gram of iron in just a big cube like this, we put it in the water, okay? It is going to displace that amount of water. All right, so let's just say this was 10 centimeters by 10 centimeters by 10 centimeters, which would give you 1,000 milliliters. Okay, 10 length times width times height. This would give you 1,000 milliliters. And so if you put this in here, it would have a buoyant force. It would replace 1,000 milliliters of water. Okay, and that weight of water, or that mass of water, would exert a force on this of, take the grams times force of gravity to change it to newtons, okay? And it would give it a 10,000 force Newton pushing up, okay? However, since this is a very large piece, it's going to have a greater force of gravity pushing down on it, okay? Now, if we have that same piece of iron and we squish it out to make this shape, it has the same mass, so it has an equal force of gravity pushing down on it, okay? But whereas this one only displaced this bit of water, this one can displace a greater volume of water, which means that means there's going to be a greater buoyant force on it, acting upward on it. And so the buoyant force has to do with how much water it displaces. If it displaces a bigger volume, then there's going to be a bigger buoyant force pushing on it. And if this buoyant force is equal to the force of gravity, then the object will float. Okay, and so sometimes people say, well, the boat is less dense because now you have iron and air in here, and that's sort of true. Okay, that's basically true, but really it has to do because it's displacing more water than it would as just this shape over here. Since it's displacing more water, then there's a greater buoyant force, and now the buoyant force is equal to the force of gravity pushing down, and that causes it to float. All right, another way to look at this, if you have a boat that's floating in the water, okay, it sinks a certain distance into the water until it displaces enough water. Okay, we have the mass of it pushing down, the mass times the force of gravity pushing down on it. Okay, and that's pushing it down, but as if you were to lower the ship into the water, as it goes into the water, it begins to sink into the water, and it displaces more and more water. As it sinks and it displaces more water, it gets more and more buoyant force. So when a little bit of it's in the water, it gets this. As more of it sinks in the water, it's displacing more water. So until it is completely in the water, underwater, it's going to increase buoyancy as it lowers in there. Eventually, it's going to reach a point where the force of gravity and the buoyant force of the water equalize. Now, if you put more cargo into this, now you have more mass, therefore you multiply more mass by 10 and you end up with a greater force of gravity. So once again, as you load more stuff on here, it begins to sink lower. And once again, though, every time you add more stuff, that increases, it displaces more water because it's sinking down lower into the water. And eventually it gets to the point where it has enough buoyant force because it's displaced so much water that it equals the force on top, the gravity pushing down on it, and so it ends up and it reaches kind of an equilibrium and will float at that level. All right, and it will continue to do that if you continue to put stuff into it. Now, obviously, there are some limits to that eventually. Okay, for example, in this example, the canoe at this point has displaced enough water to equal the weight of the canoe, and so the force of gravity pushing down on it and the buoyant force pushing up is equal. If the hippopotamus gets into it, it sinks lower, which makes it displace a lot more water, which increases the buoyant force, and to the point where, just barely, it will keep the hippopotamus afloat. Now, if his friend the alligator jumped in here, that would pushed it down farther, which would displace more water until the water started flowing into the top of the boat, and then it would sink, of course. Okay, but as long as the boat is above water, and you add weight to it, it will continue to sink in the water, which displaces more water, which increases the buoyant force, and eventually it will balance those two and sink. If it weighs too much, though, eventually its greater density and its greater force of gravity will eventually cause it to sink and continue to go down to the bottom. One last check. If we have a beaker full of water and we stick a piece of wood in it and it causes water to overflow, what's going to happen to the mass that the scale is measuring here? Okay, or the force, I should say, the newtons that the scales are measuring. And the fact is that this wood is going to sink until it has displaced water that weighs the same amount as the wood. Okay, and so it's going to have exactly the same force pushing down on it because it's pushed out just as much water as was in here before. Now, if I had a heavier object, it would sink lower and before it reached equilibrium where the buoyant force is equal to it. So that's why heavier objects that may still float are closer to the top of them, might be closer down here to the surface of the wood. Now, if you had balsa wood, which is very light wood, then it would probably float up a lot higher because it would not have to displace very much water before the mass of the water it displaces would equal the weight of the wood, and so it would just barely sink into the water. All right. All right, and one last thing before we leave buoyancy and move on to air and look at some things about it. This example is you have let's just say a metal cube, okay, and it's sinking in the water. And the question is, what happens to the buoyant force to this metal cube as it sinks farther and farther down into the water? What happens to the buoyant force? Does it increase, decrease, or stay the same? Well, good question. Glad you asked. Here's what we're going to do about it. Remember, the buoyant force has to do with the amount of pressure on it, or the difference in pressure between the top and the bottom. We said that the top has less pressure because it's less deep in the water. The bottom, because it's deeper in the water, would have a slightly bigger pressure. Okay. As you go down farther, what's going to happen to the depth of the top? It's deeper, so it's going to increase. What's going to happen to the depth of the bottom? It's also going to increase, and so forth. Okay, but the buoyant force is the net difference between those. Okay, if you subtract those two, and so if you take this one and that one, the difference between them, I can't really draw it. I'm just going to draw a little line right here. Might just be that much. Now, this one's getting deeper now, so it has a greater pressure, but this one's also getting equally deeper, just as much more deeper than that one was. So if you subtract them to, guess what? You're going to get about, whoops, that much. I missed it a little bit there. Let me draw a little tail past it. Okay. And same thing here. This one's getting deeper, so there's more pressure on it, but this one's getting deeper, so there's more pressure on it. And once again, the difference between them stays about the same. So the buoyant force stays the same as you go down because, yes, the pressures on top and bottom increase as you go down, but since they're both increasing, they kind of cancel each other out. And the difference between them, the net force, which is the buoyant force pushing up on it, is about the same all the way down. All right? And so the buoyant force of an object, once it's underwater, okay, now if it's sinking into the surface like we talked about a boat earlier, then yes, it will continue to displace more water, and that will increase the buoyant force. But once it's under the surface, it's not going to displace any more water. Okay, and so the buoyant force is going to stay the same and will not increase. The two forces on top and bottom will, but the difference between them, or the net force, will not. All right, well, stay tuned for the next video, and we will get to air.